So if we were to pick, let's say, a position here in the laminar region, let's call this position A. And we pick a position B in the turbulent region. And we plot the velocity as a function of time for these things. So here we, at location A, let's do a plot here. So this is for A. So this is going to be velocity at A. And then this axis is time. So if we plot velocity as a function of time at A, what do we expect to see here? Yes, constant. So I'd pick some value, draw a line, make it nice and straight. It's constant, it's not changing, right? The only processes, any instability that would occur naturally here is suppressed by the shear stress in the fluid. Right? The shearing of the fluid has an effect of suppressing any sort of chaotic behavior. Once the momentum gets high enough in B, that's not the case anymore. So if we plot here for B, I'm so glad this program lets me write straight lines. So if we plot here at B, what is this velocity going to look like? Just let's say the U velocity is a function of time. Yeah, fluctuating. But it's kind of important. So it's going to fluctuate. So we'd see like something like this, right? But it's going to maintain an average velocity that's constant with time. So at any moment in time, you don't know exactly what the velocity is going to be. But if you took the average of it, on average, you're going to see that it's constant. So I could look here, draw, take the average over time, and it would perfectly oscillate around that average velocity as a function of time. All right. If you take your time scale too short, it wouldn't. You'd see some moving average. But if you take a long enough time horizon, it's gonna go to the average. By the way, this position here, I guess I have been a little careless. This transition point is called X critical. That's the position at which it will transition. Again, not a specific location. There's kind of a region, but when we're modeling it, we'll kind of talk about it that way. All right. I think the best way to, I think a lot of you are familiar with turbulent flow, but maybe don't spend time Googling videos for turbulent flow. So let's take a quick look at a video. It's just kind of actually one that Greg found, but I thought is also pretty cool. So hopefully this works. Yeah, so let's see. So, okay, I'll just let you watch it here. This is there's like a rectangular pin and crossflow. So this is flow over a pin, but you'll see it in a second here. So yeah, I mean, one of the things that you can kind of pick out from that is that if we're talking about if we're talking about energy transport and momentum transport, if you're limited to sort of molecular processes, that is, the transport of energy, the transport of momentum has to do with adjacent, atoms or molecules bumping up against each other and transferring that momentum. That process is a lot more slow. It's a lot more limited than it would be if you just have a bulk of fluid, some little piece of fluid that's actually moving in the y direction, right? That transport of fluid due to motion in the y direction is orders of magnitude more important than the diffusion when it comes down to it. So we can write out some kind of observations about laminar flow and turbulent flow. In laminar flow, right, transport in the y direction is primarily due to molecular diffusion. So you'll hear about these things like the molecular conductivity or the molecular viscosity. What we're talking about there is we're limiting the mechanisms of transport to interactions between molecules, vibration, transfer of electrons, that kind of thing. That's molecular properties. Bulk flow properties or turbulent properties are basically effective properties. They are now trying to include the fact that you have bulk fluid motion, not just the molecular interactions. Okay, so again, in laminar flow, y-directed velocity is small. There is a y-directed velocity, but it's small and controlled. In turbulent flow, the y velocity is not small, and you get these eddies, and that actually tends to dominate the properties. So yeah, we'll talk about effective properties here. So we write out the boundary layer growth here. In terms of these equations, these are ones we've seen before. We'll say the boundary layer is going to grow according to the diffusion law. It turns out we can actually write the same equations for turbulent flow, but we have to change something about the equations in order for them to be accurate. So let's see, if we write this out, let's say delta M turbulent, the momentum boundary layer growth is going to be approximately 2 times the square root of mu over rho times time, but it's not mu, the molecular property, right? It's the effective property. So this is going to be something called mu turbulent. Sorry, I'm really small. Mu turbulent would be the property, and that doesn't really have anything to do with the molecular property. It's a completely different property. It's an effective property. But still, we can say that on average, the boundary layer is going to grow according to this effective property, right? On average. We could do the same thing for delta T, turbulent. There, it's going to be about 2 times the square root of, now it's going to be the effective conductivity, K, turbulent, over rho times C times T. And so mu and K are the things that actually change in laminar and turbulent flow. Density is not changing. This is maybe an incompressible flow. Specific heat's not changing. It doesn't depend on fluid motion. Right, so we have these two properties now that we have to start thinking about that are going to be different from the laminar region, which are just mu and K, right? And just to be clear, right, so K turbulent is much greater than regular molecular K, and mu turbulent is also much greater than molecular mu. Hopefully the K one really makes sense, right? Because you're effectively moving heat due to bulk fluid motion. So that's, you can see it's moving energy. Mu is maybe not quite so obvious, but if you think about, okay, we know that the turbulent layer is growing much more quickly in the turbulent region than the laminar region. It becomes clear that mu, the effective mu has to be bigger, right? Because the layer is growing more quickly. Okay. Questions on that? Pretty straightforward. Okay. So let's talk quickly about the viscous sublayer. It's kind of like anatomy of turbulent flows here. So we have over here, we have this thickness being delta M laminar, right? That's our laminar momentum boundary layer thickness. At this region, this transition here, you have these eddies that are forming, right? All in this region up here, you have these sort of eddies that are circulating around chaotically. But you actually get this little sublayer that forms right next to the wall. So this layer will start growing like this, and it'll track down, and then you get this very thin little layer that grows very slightly as a function of position X, but this is called the viscous sublayer. This layer is actually the most important thing in terms of heat transfer and shear stress when we're modeling it. And why is that? Well, if we think about what's happening here, so as you get closer and closer to the wall, there's a couple things. One, you have the wall is providing a sort of consistent shear force against the fluid. So right up next to the wall, there's a tremendous amount of shear compared to the rest of the flow. Once you get away, this is like bulk motion. So right next to the wall, there's all this shear. It's suppressing these eddies that are occurring in this instability. So you have this very laminar layer right next to the wall that forms. And if that's the case, and you think, okay, all I have to do if I'm a packet of heat and I'm on the surface, all I have to do to get out into the free stream is basically get through this laminar sublayer to the turbulent or the eddy regime, where then I very quickly can move, right? So the main impedance to motion of heat or diffusion of heat from the surface outward is going to be caused by this viscous sublayer. Right? Same thing for momentum. A little harder to think about, but there you have almost the entire velocity gradients isolated right within that sublayer. Right? That's where a lot of the velocity is happening. So this here, let's call this this thickness is delta Vs. This thickness here is going to be delta T. Let's do this in terms of momentum. So delta M turbulent. That's this full boundary layer thickness from the wall out to the edge of the boundary layer. Viscous sublayer is just the little bit in there. Let's see if there's anything else here. Yeah, so in terms of the size of this thing, it is very small. It's very small compared to not only the turbulent boundary layer, but it's also small compared to the laminar boundary layer. So just keep in mind that if you're to kind of order these things, the viscous sublayer is the smallest. That's going to be much smaller than the laminar, which is also much smaller than the turbulent.